In this video, video 3 of looking at random variables and probability distribution functions, we're going to start looking at the examples. So in this one, we are looking at example 1. So let's read it together. It says, let's let x be the random variable that represents the number of sixes obtained when a die is rolled 3 times. And we want to tabulate the probability distribution for x, in other words, make a table, and it says, and display the results in a table. So since we're rolling this die 3 times, really the best way to represent this is going to be with a tree diagram. So let's start over here. All right, so we're going to roll the die 2 times. It's just a regular die. So I want to point out that you could start out and just say, well, I could get a 1, 2, 3, 4, 5, 6, and then each of these branches will have 1, 2, 3, 4, 5, 6 coming off of it. So we're going to end up with 36 branches. That's quite a bit. So I just want to point out that in this one, there's actually kind of a clever, shorter way to do this. And that is really the only thing we're interested in counting are the number of sixes. And so what we can do for each of the rolls is just say, here's the probability that you get a 6. Here's the probability that you don't get a 6. So that's what we're going to do, is start out here with 6 and not 6. I want to make sure that I leave myself plenty of room for the tree. So this is our first roll. All right, well, we know that to get a 6 on this diagram, or I'm sorry, in this experiment, because we're rolling a regular die, is 1 out of 6. And then the probability that you get not a 6 is 5 out of 6. All right, then on the second roll could be either, again, a 6 or not a 6. And same thing here. It can either be a 6 or not a 6. And then for the third roll, again, it's either a 6 or it's not a 6. Same thing here. It's either a 6 or not a 6. 6, not 6. 6, not 6. It's pretty boring here, doesn't it? Watching all those. All right, so now let's branch off on the other ones because we're trying to find the probability distribution. Why don't we, actually, before we do that, let's figure out what those values of x are. Remember, x is supposed to be the number of sixes obtained when a die is rolled 3 times. So if we do x equals these different values, we can see here this is going to be 3, because on this branch I'm going to get a 6, and a 6. On the next branch I get 6, 6, and a not 6, so that's 2 sixes. On the next one I get 6, not 6, 6, so that's also 2 sixes. On the next one I get 6, not 6, not 6, so there's 1 6 on that one. All right, then the next one is going to be not a 6, 6, and a 6, so there are 2 sixes there. Not a 6, 6, not a 6, so there's only 1. Not a 6, not a 6, 6, so there's only 1 there. Not a 6, not a 6, not a 6, so 0 there. All right, so we can see then that our sample space for x is going to be the values 3, well, let's put them in order from smallest to largest, 0, 1, 2, or 3. So now if we want to make the table of values for this, the table would go like this. We would have x, and then we would have the probability that x can take on those values. So the values are 0, 1, 2, and 3. So now we need to go back and calculate probabilities. Well, remember, this is still 1 6, this is 5 6, this is 1 6, this is 5 6, 1 6, 5 6, 1 6, 5 6, 1 6, 5 6, 1 6, 5 6. Okay. So the probabilities for those branches, remember, these are independent, and we learned they're independent from each other. In other words, the die for roll 2 has nothing to do with the die for roll 1, or the roll for die 1. And so we can multiply these together. So 1 6 times 1 6 times 1 6. So we want the probabilities here is going to be 1 6 cubed. The next one's going to be 1 6 times 1 6 times 5 6. So 1 6 squared times 5 6. The next one's going to be 1/6 times 5/6 times 1/6. So 1/6 squared, whoops, times 5/6. The next one is only 1/6. So 1/6 times 5/6 times 5/6. So it's 1/6 times 5/6 squared. All right, the next one we have not 6, 6, and 6. So that's going to be 1/6 squared times 5/6. The next one has 2 not 6s and only 1/6. That's 1/6 times 5/6 squared. The next one is not 6, and 6. So that's 1/6 times 5/6 squared again. And then the last one, all 3 not 6s, 5/6 to the third. So if you want to change those into decimal form, which are not decimal, but fractional form, which is not a bad idea, the first one turns out to be 1 out of 216. I'll let you verify these. The next one is 5 out of 216. The next one is also 5 out of 216. And I want you to notice that the two that you had 2 outcomes for, or that you had 2 sixes, sorry, were both 5/16. And then this one also is also going to be 5 over 216. I think I said that wrong. All right, the next one is going to be, I'm going to use a different color to squeeze that in. Oops, let's do green. The next one's going to be 25 2/16. And that's the same thing with this one, 25 over 216. 25 over 216. And then the last one is 125 over 216. So if I want the probability that x is 0, there's only one way that that can happen, and that is 1/25 over 216 of the time. To get a 1, though, there were 3 different ways to get a 1, here, here, and here. And notice I can add those up, and I end up with 75 over 216. If I want to get 2 heads, you can see that there are several different ways to do that, here, here, and here. So those add up to 15 out of 216. And then the last one, there's only one way to get 3 6s, and that is 1 out of 216. So that was the first part of that. Actually, that's it. All right, they just wanted us to tabulate the distribution for x and show it in a table. So we've done that.